Okay, so we're going to prove this fact, the following fact about limsups of sequences, and here it is. So we're saying that if you have a sequence that converges to a positive real number, let's highlight that. So we're assuming that S is a positive real number. Then for any sequence T sub n, we'll have the following equality. So equality will be that the limsup of the product is equal to the limit times the limsup of Sn, of Tn, sorry. Now, the way we're going to prove this inequality is kind of two ways. First, we'll show that the limsup of Sn(Tn) is greater than or equal to S times limsup of Tn, and then we'll show the opposite inequality. So for this video, I am going to assume that, let's see here, so we're going to set beta equal to the limsup of T sub n. And now we have three different cases based on whether beta is a real number, is positive infinity, or is negative infinity. So we have three cases. Beta is real. Beta is plus infinity, or beta is minus infinity. For this video, we're only going to focus on this first case here, which is if beta is a real number. So suppose beta is a real number. Okay, our goal is to show, our first goal is to show that limsup of Sn is bigger than or equal to S times beta. Okay, now remember that we proved that there's always a sequence, a subsequence, converging to the limsup of a sequence, right? So, but we'll say by a previous fact, and this was a fact from section 11. I think we covered it in class on Thursday. There exists a TNK subsequence of Tn such that TNK converges to beta as NK goes to plus infinity. Okay. So now we're in a situation where SNK, TNK, has to converge to S times beta as NK goes to infinity, because, so we kind of did two things here. Number one, Sn converging to S implies SNK converges to S, right? Because remember that any subsequence converges to the same limit that the parent sequence converges, to which the parent sequence converges. And then number two, remember that if you have two convergent sequences, the product of the limit is the limit of the product, right? So A sub n going to A, B sub n going to B implies A sub n, B sub n converges to AB. Remember that. Okay. All right. So these are both facts that we've proved. Okay. And we combine them together to get this right here. So our SNK goes to SB. That means that SB is actually a subsequential limit, right? So SB belongs to our set of subsequential limits of SNTN. So SB has to be less than or equal to the sup of S right? But that is limsup of SN10. And the fact that it's limsup is by the theorem that we proved, or we didn't prove the theorem, but it's a theorem from section 11 that we discussed in the class Thursday. So we'll say by a theorem from section 11. Okay, so we've shown what we wanted to show, which is that S times B is less than or equal to the limsup of SN10. Now let's show the other direction. Okay. So we want to show that S times B is greater than or equal to limsup SN10. Okay, so the first thing we want to do is we want to say that without loss of generality, okay, so note that without loss of generality, we can assume that for all n, Sn is not equal to 0. Now, why is this true? This is true since Sn goes to S, and S is a positive number. Right? So, we can just kind of draw it. So if we look at our terms here, S1, S2, S3, right? Sn plus 1, At some point, all of the terms here have to be non-negative. More than non-negative, they have to be strictly positive. Because here's 0, here's S. S is our limit. And if we look at epsilon equal to S over 2, right? Then S minus epsilon is going to be S over 2. So if we let epsilon be S over 2, then S minus epsilon is S over 2. And we can find some index n such that n bigger than n implies Sn is bigger than S minus epsilon, right? Which implies Sn is bigger than S over 2, so Sn is bigger than 0. Does that make sense? So we can start our sequence at, S sub n plus 1. And we're still in a situation where S sub n plus 1, I can do a little bit better here with our notation. So our new sequence, which would start at n plus 1, this new sequence still converges to S because it's a subsequence. And the limsup of this new sequence is going to be the same because the convergence of a sequence is not determined by the first, any finite number of terms. Okay, so that's an explanation as to why we can assume that our terms are strictly positive, right? Since our limit is strictly positive. Where was I? Okay, here we are. Okay, so now that we know, or now that we're assuming that our terms are strictly positive, we can say that 1 over Sn converges to 1 over S. Right? And since 1 over Sn converges to 1 over S, here's what we can do. We can say that by our result from part 1, the limsup of 1 over S and any other sequence is going to be bigger than or equal to, 1 over Sn, the limit of that 1 over Sn, which is 1 over S, times limsup of the other sequence, right? Now the key here, or the trick, if you will, is to use the sequence SNTN. So now this left-hand side of the inequality is equivalent to the limsup of Tn, and the right side of the inequality is 1 over S times the limsup of Sn Tn. So we just cross multiply and we get, right, because this left-hand side, that's beta, so we just get S times beta is greater than or equal to limsup Sn Tn. And that's what we wanted. So one of the hypotheses, which is that we have a positive real number, doesn't impact us until we want to show the second part of the inequality, right? So we split up this equality into two inequalities, this one and then this one, right? So just as a reminder, you always want to go back and be aware of how you are using the assumptions or the hypotheses in your proof. And that's it.